very much for inviting me. It's a unique honor, and I want to thank Professors Fulton and Chu for getting me to this wonderful meeting. Now, I will be giving two talks. The first one is general, and the second one is very specific, would be strictly about how to teach two topics. Do you hear me?
Yeah.
But the first one would be general about basically why the Common Core standards in mathematics were written and what is so different about them. Let's just do this first. Yeah, there we go. So first of all, the Common Core standards were written in the face of a need to do something, some improvement for our mathematics education. There was a crisis, and of course your first question is, what crisis, right? So I want to give you a very brief idea that what the crisis is, or the magnitude of the crisis. Let's look at one of the items. NAEP, I guess everybody here knows what NAEP is, National Education Assessment Progress. Everybody knows this. NAEP. This is the nation's report card. It comes out every year. Every 4 years. I'm a little bit hazy on that one. But the Congress is mandated by Congress. It is controlled not by the White House, but by all, both Congress and the White House. It's sort of real governmental unit. And goes around, it does sampling of all the states, and then they give report on every state's achievement. And in 1978, the 8th grade, now I want to emphasize the fact it's an 8th grade problem. They ask this, estimate this. And of course, you take one look, you know exactly what the right answer is. Yes? Yeah? Okay.
I don't know.
Right. That's the correct answer. That's correct. Everybody knows that. Now, but the percent of students who got it right, 8th graders, I'm not talking about 5th graders, 6th graders. These are middle school students. Only for 24%. Now, think about it. Suppose we do it at random. Five questions. The norm would be 20, right? That means the students who could do this problem are, on average, about very little bit better than random sampling. 8th graders. So you say, well, this is old hat. 40 years ago, no problem. So I'll give you something more recent. So first of all, this is the reaction. Students say there's a big connection between basic understanding of fractions and reasoning. Anyway, students are all wrong. Students are the problem. That's this is, of course, this has been looked at by many educators, and they've written many papers on this kind of thing. So let's look at something slightly more recent. 1983, 5 years later. Army bus holds 36 soldiers. If there are 1,928 soldiers, do we have to ship them to some other place? How many buses are needed? Of course, you do division with remainder, and the answer is actually, it's correct. Yeah. That is, of course, it's the correct answer. 31, remainder 12, yes. And so the 29% of the students said you need 31, remainder 12 buses. The correct answer, of course, is 32. That one. And 30 didn't even get it right. Did not even get the arithmetic right. Now, so in summary, other than the 23% who got it right, 77%, no, 8th graders could not do that problem correctly. 77%. I hope you think that's a crisis. Yes? And so, of course, again, educators had their opinions, and the students learned their counterproductive behavior in their mathematics classes. They didn't say how, but they just said students, again, they're not doing their job. They didn't learn it correctly. Again, students are a problem. So you say, well, 1983, that's 35 years ago. No, that's still too old. Right? So let's do something slightly more recent. 1995 TIMSS. Now, TIMSS is one of the two major international assessment units. The other is PISA. They assess the national achievements of many, many countries, not all. In 1995, they wanted students to add those three fractions. And I won't tell you what the correct answer is first, but you know what's so special. I have to get used to this technology stuff. You know what's so special about this, yes? Does everybody see it? Yeah, add the numerators, get it, add the denominators. Yeah. So the answer? 42% American students, 42% said add them on the top, add them on the bottom, and get that answer. The correct answer, but those who got it right, is less than half. In case you say, well, this is not so bad, right? So look at internationally. The top one, of course, so you should, let's see, maybe the next one. No, did I give, no, yeah, no. Yeah. Oh, yeah. Right. Maybe I forgot that. Okay, I somehow neglected to give you the international average. International average, those who got it right, is not much higher than this, 49%, I think. So international, in other words, everybody's screwing is just screwing up. Right? But that's not an excuse, because you have to look at what is capable. These are the three highest, not the three highest, but among the top. Japan, Singapore, well, they are much more reasonable. The percent of students who got, who chose that simple way of doing fractions at the top, at the bottom, it's single digits, 9%, 6%, like that. And those who got it right is over 80%. Now that's more like it. I don't expect 100%, nobody does. But 80% is reasonable. And so there are people who can do it right. So you say, well, this is 20 years ago, right? So let's go to something 4 years ago. 2011 TIMSS again. Again, it's 8th grade. I've been, by luck, I hit on all 8th grade items. 8th grade students. Now this is 1/3 minus 1/4. What's your guess? What's your guess that they get it right? Don't forget, A is the one that says is 1 minus 1 over 4 minus 3, which is 0, of course, right? And look at it. 32% shows that. And those who got it right was 29%. D was the correct one, right? Let me see. Yeah, D is the correct one, of course. And that's a third. 8th graders. So I hope you're convinced that there is a crisis. There has been a crisis. So we have to do something about it. Well, these are not the top, but I give you again because I mentioned those names and I do it again. Japan is not doing so well for a change. 65%. That's disgraceful. Anyway, so there's a common thread, which that most students start making sense. They don't even try. Look at the answers. I mean, they're nonsensical answers, and yet, like 1/3 or more than a fourth of the students would choose the what you might call stupid answers. Now that's not so good. That's symptomatic of something really serious. It's not a matter of saying I was careless, I didn't have enough sleep, I ate the wrong thing that morning. No, it's not that. It's more than that. So, but all in all, educators said, well, the students that are growing up, they didn't get it done, they didn't do their job. and education research agree, and students just screwed up. Is that really true? How come so many students would start making sense? We should ask that question. Yes, maybe they're all very bad, yeah, it's possible. But there's an alternative hypothesis, namely that maybe they're not as bad as we think they are, but that we taught them the wrong things. Maybe we didn't teach the things that they could learn. So why not try this? So they start making sense, not because they are bad or whatever you call it, yeah, but what we teach them, what's in the textbooks, simply doesn't make sense. Could it be possible? Let's try it. Take a look. Well, this is the carry to its logical conclusion. You'll conclude that, well, we're just teaching them the wrong thing. We're teaching them something that seems to be mathematics in the same way that margarine is butter, but really it's not the real thing. So that kind of mathematics, if it exists, I call it textbook school mathematics. It resides, for the last 40 years or so, has been pretty constant. It resides in the textbooks, and that's what students have been learning. That kind of mathematics is neither learnable nor teachable. So what those items indicate to us is nothing but the fact that you teach them the wrong thing, you expect the wrong results to come out. Garbage in, garbage out. That's the basic computer dictum. Am I right? Well, let me try to convince you, give you a few examples again. First one. This is fourth grade stuff, teaching a division with remainder. So we all say 25 divided by 7 is 3R4. Every book says that. Does it make any sense? Try 64 divided by 20. That's also 3R4. Now that's 3R4, that's 3R4. Therefore, equality, right? Therefore, 25 divided by 7 is equal to 64 divided by 20. Does anyone here believe that? But we've been feeding this. Now, has anyone here not been taught this? Raise your hand. Yeah, we've been teaching nonsense. Well, the correct way, this is not that hard because we call it correctly. 25 with quotient 3, remainder 4, that's the right way to say it. It's perfectly understandable, but we don't teach that. We teach 3R4. Now, you will say, well, that's a small thing. It's not so small. Researchers have been alarmed by the fact that students cease to understand the meaning of equality. The equal sign, there's been serious research in the last 10 years or so, no, 15. Well, the breakdown of this concept of equality. So and of course, researchers don't ask why, they say, well, we observed. When you ask why, you look at the textbooks. From the beginning, students have been taught not to take the equal sign seriously, such as, 25 divided by 7, 3R4. Equal sign means almost nothing. So researchers say that our students have trouble learning algebra. One of the reasons is that they don't even know what the equal sign means. And their conclusion, in this case, I tend to believe them, that the damage to students about the lack of correct conception of the equal sign is robust and long-lasting. Second example, add two fractions. I'll finish it now. So in textbooks, what they tell you is what? Take the least common denominator and do some monkey around with a number like this. You come up with that. Now, what's wrong with that? Well, people have memorized this. Actually, I memorized this. I look back. And so, well, anyway, so we have different modes of survival, so I survived it. But does it make any sense to you? What does addition mean? You go through 4 grades, this is done in full generality. In 5th grade, no matter how you do it, usually 5th or 6th. In New York, it's 6th, I think. But doesn't matter. You went through many grades, you come to the discipline of learning fractions, but you spend a lot of effort mastering how to add numbers. What's meant by adding number? You know perfectly well. Combine together and you count, that's it. You come to adding fractions, you're gung-ho, you say, I can do whole numbers, I can do fractions, and the sort of teacher slaps you on the face, says, don't do that, take the LCD, and you do this and then that, and you come out and answer. Well, don't ask why, just, 25 problems on this addition. How do you want to learn mathematics that way? Or how do you want to learn anything that way? Yeah, that's gone. So this is actually if you talk about learning, learning means something reasonable you accept. Now this is clearly not something reasonable that you can accept. The learning process comes to a complete halt. And after that, do you want to learn mathematics? And there's a survey, and I've been discussing with some educators. Some survey long ago saying that students, there's math phobia, you know that. And they try to locate how math phobia, what did it originate in the learning progression. And the tentative conclusion was that it happens, math phobia happens more or less right after students were taught adding fractions. Now, so continue with fraction. The fraction, of course, is a piece of pizza, right? So now, try that. How do you add 2 pieces of pizza? I mean, how to multiply 2 pieces of pizza? So that's an issue. And then now let's look at the word problem. The standard problem, like 2 trains or 2 people walking towards each other, and when do they meet? That kind of thing. I think you don't have to read through it. You see it, you recognize it. Right? That's good. You do it by doing a lot of fractions, adding, multiplying, all of that, right? So the burning question is, so how do you learn? Now, you can't make sense of this. I mean, how do you learn? So that's a very serious problem. I mean, you don't think about it until you come face to face with the kind of test results that I gave you in NAEP and in TIMSS, and you begin to wonder. Maybe it's not our students' fault. Maybe we have done something wrong. Another example. Now I don't know all of this. Negative times negative is positive. Now don't feel too bad if you have some doubt about why it's true, you have trouble understanding, whatever. I've been asked this question in Singapore, I've been asked this question in Beijing, I was asked this question in Hong Kong, all that. Total collapse of mathematics education, basically. So now the way we approach it here with the textbooks is set up a pattern, right? So let's say look at the specific problem. -4 times -4 should be 8. That should be, right? So why is it 8? So here's I think you all recognize it, the pattern stuff, right? Yeah. So you first look at this. Fix this, and you go down one by one. Every time you go down, you can notice that the product, it goes down by 3. Now the pattern should persist. Therefore, the next after this would be -1 times 3, right? Should go down by 3, so 0 goes down to -3. Another one goes down by 3 again, so -2 times 3 should be -6. That's what you find in 90% of the textbooks. Now, to figure out that -2 times -3 is -6, and so on. -2 minus 2 is -4, -2 minus 1 is -2. So it's the same argument. Now you come to, now you fix -2 here, and you lower this one by 1. You can see. Why should I be telling you? You have all seen this before, right? You don't have textbook like this? You didn't talk the wrong textbook? Yeah, most textbooks do this. And so anyway, so again, the right side goes down by 2, right? So therefore, the next one is -2 times -1 should be, well, oh no, goes up by 2, I'm sorry. Yeah? -6 goes by 2, goes up by 2. So next one should be 2. Next one is 4. Next one is 3. Next one is 8. I thought it was over 90%, maybe 80. So you should ask how your book taught you this. Right? So with similar problems, no question about it. So clearly most students don't buy this because everyone, FAQ, among the FAQs, everywhere you go, and that's the top usually. Y is negative times negative equal to positive. And so clearly we're not educating. The fact that all that comes down to is the distributive law, textbooks will not mention that. All right, another example. So this is a standard rate problem and walks briskly 3 miles first hour, then 100 miles, then she walked in 84 minutes. 84 is, of course, it's not 2 hours, not 3 hours, but you know, in between. So you do, this is called proportional reasoning, right? You do proportional thing. 3 miles is to 1 hour, 3 miles is to 1 hour, which is 60 minutes, yeah? So 60 minutes to 3 miles as 84 minutes is to X. If you walk X miles in 84 minutes, they're in proportion. You set it up, you get the answer. So let's not question this. This is supposed to be acceptable. Let's look at a similar problem. Slowly drop from 144 feet, drop 16 feet the first second is Newton, so you just trust that. And how about does it drop in 3 seconds? Well, you proportional reasoning again, right? 1 is to 16, as 3 seconds is to x, solve for x, 48 feet. Of course, this time is wrong. You do an experiment, you see that in 3 seconds it goes not 48 feet, but 144. Why doesn't it work? You say, well, you can't set up a proportion for a stone. Why not? Well, it comes down to the fact that you cannot set up a proportion until you know that the speed is constant speed. That sounds very simple, except that now I think there will be no disagreement. Which person has ever come across a K-12 textbook that tells you precisely what constant speed means? Raise your hand. Constant speed is taken for granted. That, whoa, have you ever been in the car that travels at 60 mph? Yeah, so you know what constant speed is. It's much more subtle than that. It should be carefully defined. And then when you do the problem with n, yeah, and that problem. In fact, this problem is not doable as it stands. It's not doable, completely not doable, unless you say n walks at a constant speed. And of course, you never taught that. You just taught to say proportional and so on and so on. And so now that's, well, it's another situation where we think we have taught students something, and we have not. And if they don't learn it, it's not their fault. We just screw up. Oh, so I'm repeating this. Yeah. So now look at another example. And I could go on with about 100 examples like this, but you don't have the time. But anyway, this is interesting. Similarity, similar is same shape but not necessarily the same size. You all agree, right? This is what we teach in middle school. So look at these two curves, this curve and that curve. They don't look the same shape to me, maybe to you, but certainly not to me. I'll say they're not similar. But for sure they're similar because they are both graphs. They are both graphs of, one is a graph of the left one, that's the left one. No, wait. Oh, that, okay. No, I put it there, yeah. The left one, left one is x squared plus 10, and the right one is, 360 x squared plus x. All graphs of quadratic functions are similar. It's a technical thing, it's precise, and you can prove it. Okay, now, remember the one on the left? Okay, now I give you another graph, this one. That the two clearly look similar. You say, same shape, they're similar. But this time you get wrong again because the one I just showed you, is the graph of a quadratic equation, x4. I give you precisely what it is, so no kidding, it's exactly what it is. So what is similarity? That's the problem. Now you want students, if you're a student, you want to learn about similar figures, and you suddenly find that same shape is not good enough. So what is it then? No, we failed. One more. Right? So TSM, algebra 2, this is algebra 2. Look at algebra textbook and say, what's a parabola? What parabola? Parabola is graph of a quadratic function. Few disagree with this. Yeah. So what happened is that a former colleague of mine, he's now in Harvard, one day he was very upset because his daughter came home and said, my teacher told me that the graph of this curve, x equal to y squared, is not a parabola because that's not the graph of a quadratic function. And you all know what the graph of that is. It's this one. It's the ordinary parabola turned clockwise 90 degrees. It's clearly, but the vertical line rule, you know this is not a graph of a quadratic function. So the teacher told her, no, this is not a parabola because it's not a graph of a quadratic function. And he got very upset. So I tried to calm him down. Not the teacher's fault. Don't get upset. Yeah, we are responsible collectively. We don't even get something as simple as the meaning of a parabola right. And we teach students the wrong thing. So how can they learn? So now, as I said, I really can go now. I'm not exaggerating. I can give you 100 if you give me time. But I can't go on like that. So let's just start with those 6 examples. And it gives you an overview of how bad things are the way we have been doing it. So now, do you wonder why then students stop making sense in mathematics? They don't even try. So it comes to pass that, yeah, you all know better than I do. In fact, students look at word problems, they don't try to understand what the words say. They pick up the keywords, and if something says add, something says subtract, something says multiply, something says divide. You should do those things. Now think about it. The test result about army buses or whatever, all those things, it's exactly that phenomenon. You see numbers, you don't ask what they are, you just crank out an answer by randomly multiplying or dividing or adding or subtracting. That is exactly what's been happening in many classrooms. Now, you have any doubt about what I just said? Google keywords for word problems. Keywords for word problems. Guess how many items you're going to get if you Google? 4 million. 4 million and 100,000. It's a big industry. Because why? Because that's what we teach our students, and everybody is searching for keywords, learning how to do keywords. Now that's not mathematics education. That is, I don't know, probability maybe. So kids come to mathematics. They try to do good. They want to make sense. A few experiences, a few encounters like that, you give up. They are beyond giving up. They're in total despair. They say, what? Well, no, I just randomly add and subtract numbers. And that's why you know 1/3 minus a fourth is 1 minus 1 over 3 minus 4. Well, because why? You see numbers, combine them some way, doesn't matter. Because it's not going to make sense anyway. Never makes sense to me. Teachers never make sense to me. So that's what we have right now. So there, any attempt at improving school mathematics education starts with improving the curriculum. It has to. Otherwise, it's the computer dictum. Garbage in, garbage out. But in 21st century, now in this day and age, standards drive the curriculum. You want to change the curriculum, what's the first thing you must do? Change the standards. And this is exactly where the Common Core standards come in. As I said, right, Common Core standards arose because of the need to improve, or of the ongoing education crisis. That's the crisis we're facing. Therefore, Common Core try to do something to improve the curriculum. It's not the curriculum, but it tries to improve the curriculum by dictating something. So we'll come to that. And in what aspect, in what way the Common Core standards have made some inroads in improving the curriculum. I'll give you some indications. But you understand why the Common Core standards are different. There have been lots of complaints, political complaints mainly, that they're prescriptive. They destroy teachers' creativity. Now forget it. Before you get creative, you have to be right. If you're not right, you cannot be creative. Now let's face it, that's the honest truth. So Common Core standard, you say it's too prescriptive. Well, what we think of it is trying for the first time to set the record straight, get it right first. The next step, if you all get it, we all get it right, then we can talk about creativity. We can talk about innovation. Right now, we're not at that stage. And so, if you have a set of standards that are not prescriptive, no change. I'll give you an example, just in case you think I'm lying. Right? So anyway, this is a political comment. Right? So most of the discussions on the internet about the Common Core standards in mathematics, they are non-mathematical. They pretend to be. And so they complain about, it's micromanage the teaching, nothing to do with mathematics. That's all wrong. The main thrust of the Common Core, if anything, is that it makes a serious attempt at eradicating TSN from the classroom. So if you don't do that, as I said, you're not going to be able to improve curriculum. So I give you an example. I got this on the web. I hope I got it right. Right? It's called MST Standard 3. Am I right? It was the standard before, right? What is 3 mean? 3. MST 3. What does it mean? 3. The third version? Third. Third.
The third standard in the group of standards.
Well, this is K to 12. Anyway, what I got was K. Anyway, doesn't matter. So it has 5 process standards: reasoning standard, proof standard, connection standard, strength. Sorry, they're all good. Don't you want reasoning? Don't you want proof? Don't you want connection? Yeah, no, we want all that. So this set of standards has the good things. And in grade 6, you talk about how to add, multiply, subtract, fraction, so on, so on, so on. You can't say this is wrong. This is absolutely correct mathematics. Good intentions galore. What has it done for you? Please reflect. Has it made any change in making students see that adding fraction is combining things? Has it made students feel better about what's it called? Our is not the reason why just invert and multiply. Has it changed anything? Good intentions. But because those standards do not address the issue, that outcome, that's what happens. And that's why you have to be prescriptive at this point, because you want to right the ship. Now, about reasoning and connections, right? Reasoning, right? So, as a result of MST Standard 3, have you seen an increase in reasoning in your textbooks in teaching fractions? Has the MST Standard 3 increased your perception of the connection, the tight connection between fractions and whole numbers? That is the key about learning fractions. That fractions are essentially the same numbers as whole numbers. They're not different numbers, as most believe. So, good intentions. You didn't put it on paper. Not good result, because this is not prescriptive enough. That's the reason. So, for example, just quickly go through it, and we will go through it more in detail in the next hour. Right? So, about adding fractions. In grade 3, it begins the progression towards adding fractions. In a simple case, first get fractions on the number line, and equivalent fractions in simple special cases. That's the first round. The second round, in grade 4, you add fractions with the same, same denominator and so on, and then simple equivalent fractions. And this is the key part. Define adding fractions and joining parts referring to the same whole. Now, what does that mean? Well, I'll give you a quick tour of this. Well, anyway, I come to that. But grade 5 ends the discussion of adding fractions. And, well, I'll let you read because you can be there, then I can talk about it. As I said, I'll go through this in greater detail, but the main point is that the Common Core standards, there's something different. First of all, it's not one grade, like in New York, it's 6th grade. No, it's 3rd grade first, you learn a little bit, prepare you psychologically for it. 4th grade, a little bit more, and 5th grade, in full generality. And yeah, and then you end up with this correct formula for adding fractions. So though, in very rough terms, what's meant by what I mentioned about this joining parts referring to the same whole, what does that mean? Well, you have to learn how to interpret, right? Once you know fractions represent the length of segments, joining parts, that means lump them together, well, concatenation, that's my favorite term. Concatenate them, and then look at the total length. What's the total length? By definition, whatever it is. I don't know what this length is, but we call it the sum of the two fractions. It is combining things. Adding fractions is combining things. All right? And of course, once you know that's the meaning, you can sit back, relax, and figure out a way to get the formula. That's the correct formula. There's a reasoning to it, and we'll come to that in the next hour. But the key point is that the way Common Core does it now is not just say, here's a formula, LCD, and go home. Not that. But first, it tells you, what does it mean? No formula. Just say, what does it mean? What is it? What is it? In mathematics, we don't do anything without first knowing what it is. So you have the first thing is know what it is. And then you use reasoning to get at the formula. There's a separate step. Don't lump the two together. And finally, you notice that there's absolutely no mention of LCD at all. It restores the meaning of adding fractions. Right? So look at that, another example. Decimal. Now that's another horror story, right? Fractions and decimal. Every educator will tell you that non-learning in fractions and decimal is sort of proverbial. So now, what is the correct meaning of a fraction? Of a decimal, sorry. A decimal is a fraction whose denominator is the power of 10. So for example, this is a decimal, that's a decimal. Or you're shocked and you say, well, no, that's not a decimal. You're right and wrong. This is not the way we write decimals. But this is correct about what a decimal is. That's exactly what it is. A decimal is a fraction. So what happens? Well, it happened before you were born, 1600 or so. A Vatican astronomer, German by birth, Christopher Clavius, in year, I forgot. 1593, I got it down right. 1593, he said, why do you write such complicated objects? You can simplify it to, no need to do that, no need to do this, just 7.35, where the dot indicates that there are 2 zeros. Now, similarly, so let's look at this one, right? So there are 5 zeros on purpose. I hope, got it right, 5 zeros. So this is the decimal point 5700. The decimal point is 5 decimal digits from the right. Now, because it's 5, and therefore you have to add the 0 there to indicate this 5 0, right? 0, 5. That's a latter-day interpretation of that fraction. The original meaning of fraction is a fraction. What we call fraction today, by the way, I don't know how many of you know this. These were the only fraction considered by most people, by the Chinese, for example. They were fractions, 1/3, 3/5, and all that. They were not called fractions. They were called vulgar fractions. Right? These are the honest fractions. Now, okay. So now, of course, that's why you were surprised when I said a fraction is, a decimal is a fraction of a particular type, because this is what you were taught. 0.209 is 2/10, 0 hundredths, and 9 thousandths. And it sounds so soothing and so nice. What does it mean? Of course, this is a T, right? Wow, so this is what? 1/10 to 20 thousandths, 400 thousandths, 5 millionths. Anyway, it's Kafkaesque, right? Forget it. This is why we don't teach decimals correctly, because we only teach decimals with 3 decimal places, because tens, hundreds, and thousands, and those are still within the realm of common sense. But beyond that, you don't teach it because, well, you can't, because it's just too clumsy, right? And so, but to us, of course, what is this decimal? Simple. That's exactly what it is. 9 zeros at the bottom. That's it. So what's wrong with this? This way of saying tens and hundreds and thousands and so forth? What's wrong with it? Well, I tell you what's wrong with it. Because you separate fractions, decimals from fractions. You say fractions is one thing, because as you know, I don't know how many of you disagree, right? Textbooks teach decimals separately from fractions. So parallel development, as if at some point they say, well, we'll convert one to the other. But at the beginning, you just, dollars and cents or whatever. That's wrong. A decimal is a fraction. You have to face up to that. Yeah. So what ultimately is wrong with that? Well, because it hides the truth. You say 7 and 3/10 and 500. It sounds good, but what does it mean mathematically? Because after all, mathematics is about computations, about numbers. What number is this? How do you compare with 7? How do you compare with 3/10 and 500? What does it mean? And it's addition. So you want to understand what this decimal 7.35 is, you have to first understand how to add these fractions. Unfortunately, you teach decimals independently of fractions, what do you get? Well, students learn decimals, they don't know what it is. They say, 7.35 is all these tidbits floating around. There's a 7, there's a 3, there's a 5, and suddenly someone says, look at that decimal. You say, what decimal? There's a collection of tidbits here. The conception is all wrong. So you want a decimal with a single number, but the way TSM teaches fractions does not allow students to conceptualize a decimal as a single number. It's always tidbits, tens, thousands, 10,000, millions, whatever. And my personal guess is that this fragmented conception of a decimal accounts for a lot of the non-learning in fractions, in decimals. So you know these are the horror stories, right? 0.098 is bigger than 0.2 because 98 seems bigger than 2. And this is, I got it from the research literature. They're going hot wired about things of this nature. Yeah, so what has TSM done for our students? Well, TSM has not even spread the correct message. Forget about teaching not less than optimally. Forget that. Just the basic requirement of conveying truthful information. That litmus test, TSM fails completely. And of course, not just in fractions and decimals, all over. And of the 6 examples are typical examples. give you an idea overall of what textbook school mathematics has done to students. So coming back to Common Core standards a little bit, so this is one of the things clearly addressed in the Common Core. Fractions, by definition, you're looking at specific standards in grade 4 and grade 5. A fraction, a decimal is a fraction. That's the precise meaning, and it goes on there. So you say, what, is there any advantage in this? Was that a big deal? Well, yes, because first of all, as I said, this allows you to see decimal as a single number, but much more is true. Let's look at, for example, multiplying decimals. Now, there's a rule, right? How you multiply this? TSM says, multiply the whole numbers, never mind the decimal point. So let's multiply them. Then after the fact, you say, you put a decimal point where? Well, you have 5 decimal places here, 2 decimal places here. 2 plus 5 is 7, so you move it 7 digits, so it's 1, 2, 3, 4, 5, 6, 7. So that's how you multiply decimals. Why? Well, TSM is not very interested in the whys. Generations of students have memorized this rule without knowing why. I think to this day, they come out of school, probably still don't know why this is true. Not for, to us, it's very simple. A decimal is a fraction, right? So when you say multiply those 2 decimals, you're multiplying 2 fractions. You multiply fraction, you have to know fractions, of course. The basic fact you have to know about fraction is the so-called the product rule, which is very simple. Everybody believes this. Although this is part of the Common Core that you're supposed to prove this, and that's not so simple. But I'm not here to talk about that today, so I skip that. Just take for where you're going to use it, and so you multiply this. So this is the product of the 2 fractions. You know how to multiply fractions. That really is the ideal world where you multiply the top, multiply the bottom. Now, when you come to here, that's exactly what TSM tells you. When you multiply decimals, never mind the decimal point. Just multiply the whole numbers. That's exactly what we're doing in the numerator. Down there, you see 10, of course, 5 zeros and 2 zeros altogether is 7 zeros. Downstairs, 10 to 7 power. And therefore, by our definition of a decimal, that means what? You put 7 zeros up here. And that's the reason why you multiply decimal in that particular form. So you can see advantage right away. In doing things right, because you do it right, you can at least make it reasonable. If you make it reasonable, you can explain it. Then at least you're making it possible for students to learn. I'm not guaranteeing learning. I'm just saying you'll make it possible for learning to take place. The rest, of course, is up to the students, up to the teachers, and up to schools. So now, of course, all that is predicated on the fact that fractions is done correctly. And on the whole, Common Core has done that. Fractions, the subject of fractions is done correctly. Now, so we have spent a lot of time doing this sort of thing. But I want to address one other aspect of the Common Core, which is supposed to be very popular, very important, very crucial part of the Common Core math standards, namely so-called practice standards. This is sort of billed as the heart and soul of the Common Core standards, the most important part of Common Core, sort of. I would like to present you a proper perspective on the practice standards. What are they? What do they mean? Is this the right way to plaster all the Common Core practice standards across the walls of your classroom and make students recite them and memorize them and show that this is what they're learning? Well, let's see. So we begin from the far right field, so to speak, and we step back and say, okay, so you want the Common Core because you want good curriculum. So what are the basic requirements? What does a good curriculum look like? I've described to you, at least mathematics, of what a good curriculum should look like. The 5 basic requirements. Now, my time's running out, so I'll be a little bit fast. One is that every concept has to have a definition. It's very, very painful. Ask any of your students that they are asked to do things without knowing what they are. It doesn't happen. Nobody learns that way. So you have to give definition. And second, so for example, what's a fractions and pizza? So you can see what's wrong with pizza, right? With the problem with the trains or whatever, and you certainly say, I'm supposed to compute with them, but what did the pizzas disappear into, right? Thin air or something. You have to give definition. The second one is that you have to have precision. And the common thing about, a good example of lack of precision is that even in the old way of doing pizza, even doing it wrong, but you have to do it, I don't know how to say it, but even if you say a fraction is a pizza, at least you do it right, do it precisely. The whole is not the pizza, contrary to what you think. The whole is the area of the pizza, not the shape. So they couldn't even get that right. Now, so this is specified in the practice standard. Oh yeah, so I should point out too, yeah, you saw this. Practice standard number 6 says you need definition. And the other part of practice standard 6 says you have to be precise. Use it consistently. And so the division with remainder 6R4, whatever that stuff, well, this is basically forbidden in the practice standard 6. You have to use the equal sign precisely and persistently. A third requirement is that everything must be supported by reason. You have to be able to explain everything. So that goes without saying. The fourth thing is mathematics is coherent. Whole numbers and fractions and negative rational numbers, so to speak. They are all really part of all of a piece. You should present the students that way. And so in Common Core, in the standard 7, look for and make use of structure, and practice standard number 8, look for and express regularity in repeated reasoning. They are hinting at this coherence of the mathematics. That curriculum should reflect on this coherence. And this one is purpose. You know, mathematics is not done for fun. Mathematics is always done with a specific goal in mind. Mathematics, like all sciences, is extremely goal-oriented. We don't do something just for the fun of it, but we have something in mind. We want to solve a problem. So if you can present that to students, you get a lot more buy-in, you teach better, and they learn better. I can illustrate this later on. But so a good curriculum would meet these 5 standards, but in the process, you see, what happened is that you want better standards because you want better curriculum. You want better curriculum because what? Because better curriculum would inspire better student learning. And so your question is, what is better student learning? What does it mean? Students are learning better. So with the practice standards, they are here to tell you, you want to detect better learning? What signs can you use to detect the learning, the good learning? That's what the practice standards. 8 of them, they tell you, if good learning is taking place, you can detect at least the 8 among the observable behavior that you can see among students. So ideally, so teachers teach better, and then get implemented, and then you observe that, oh, the students are actually exhibiting the behavior described in the 8 practice standards. So the practice standards basically tell you the ultimate goal of education. Of course, education is not about great mathematics, great standard, none of that. All that are means to an end. The end is what? Students learn better. And the practice standards tell you that's the goal. That's good. You should know the goal. Everybody should know the goal. But do you want to be fixated on the goal? Do you want to really keep a constant tab on the practice standard every minute you teach? I mean, this is so common now. Every lesson is plastered with 5 standards. They're distracting. Don't do it. Because why? Think about it. I'll give you an analysis. Now, any NBA fans here? No sports fans? Wrong audience. Okay, sorry, but But you heard about NBA playoff. Right? Everybody wants to win the championship ring. Ask any player, ask any coach. Do you just think about the championship ring? Forget it. They tell you no. Our nose is on the grindstone. We just go out and play hard and forget about the championship ring. That's something you win at the very end. On the last day, they would think about it. They would dream about it. But right now, play hard. Our teachers, yes, want to achieve the practice standard. They want to play hard. They want to. Have we equipped them to play hard? Can they shoot the three? Can they block shots? Have we taught them how to do those things? We haven't. They cannot play hard unless they know the mathematics in the Common Core standard. We have to give them this kind of knowledge. And the education establishment is guilty. Yes, is guilty because we have taught our teachers CSM. Now we ask them to teach the Common Core standard with the goal of driving out TSM from the classroom. That's not reasonable. In the same way that we ask students to achieve, to do well on the TIMSS test and NAEP test, and yet we feed them only TSM. That's not possible. So that is the most urgent task in front of us. How to equip all our teachers with correct content knowledge. So we should all contribute. If this is a big task, no guaranteed success, but this is what's in front of us for the implementation of Common Core. And that, I think, is probably what do you call it? Task number one for all of us in mathematics education. Thank you. Thanks, Sally.